Good day everyone, I'm Ton Pham from the University of Melbourne. Today I'm going to present my work on smart Greybox fuzzing. This is my joint work with Marcel, Andrew, Alec and Abik, who are currently at Monash University, Veracode, UiPath and the National University of Singapore. This is one of the first works making Greybox fuzzing input structure aware, and this is dedicated for chunk-based file formats, which are common targets for attackers. Our findings show that there are hundreds of CVs found in programs taking chunk-based files every year, and the number keeps increasing. In today's talks, I will first identify the limitation of the current Greybox fuzzing approach in handling chunk-based file formats. Secondly, I will present the smart Greybox fuzzing approach and the tool that we implemented. Lastly, I will talk about some experimental results showing the effectiveness and efficiency of our approach. This is the common workflow of traditional Greybox fuzzers like FL. It takes a seed input from a so-called input queue, slightly modify it to generate a set of mutated inputs before sending them to the system under test. If a mutated input can trigger a new behavior of the system under test, like a new branch or new program crash, the input will be retained for further fuzzing round. However, the approach has a critical limitation. It has no information about the structure of the seed inputs. Specifically, it views each input as a bit string, and hence it does randomly apply low-level mutation operators on the bit strings, such as bit flipping, inserting boundary values, or random insertions or splicing of another input string from another input. Because of that, the technique doesn't work well with programs taking highly structured inputs like chunk-based file formats. In this slide, I show a tree-based representation of the PNG image file. We can see that a PNG image can be represented as a tree in which nodes are data chunks, and each data chunk contains several data fields, and there are internal constraints between the fields. The low-level mutation operators could quickly invalidate the constraints and make a valid file become invalid. Moreover, it is very unlikely that these mutators would produce valid chunks for the image. To address this crucial limitation, we designed smart Greybox fuzzing that makes Greybox fuzzing input structure aware by doing four things. First, we change the input representation from bit string to a tree-based representation. Second, we design a set of new mutation operators that work at chunks level. Third, we prioritize more valid inputs. To make this work and retain the fuzzing speed, we also apply several optimizations. First, let me talk about the new representation. We design a high-level structural representation called virtual file structure. The data structure consists of chunks and attributes which present the data chunks and data fields. Each chunk can be the parent of another chunk. Moreover, for each chunk and attribute, we maintain the start and end indexes, which allow us to map them back to the physical file and input. Based on this data structure, we design a new component for Greybox fuzzing. We call it FileCracker. This component takes a seed input along with an input model which is written in XML-based format, and it will transform the input to a tree-based representation. Moreover, this component can also output the validated score of the input, which is used to improve the selection algorithm of the fuzzing process. Specifically, more valid inputs should be selected more frequently. You may have a concern about the manual effort needed to write the input model. However, in our paper, we presented a guideline which allows users to write input models faster and in a more systematic way. Since we can represent the inputs in a high-level tree-based structure, we designed a set of new mutation operators which can work at the chunk level. Specifically, we designed the chunk deletion, chunk addition, and chunk splicing algorithms. We evaluated our approach in comparison with state-of-the-art in Greybox fuzzing smart black box fuzzing, and 10-based Greybox fuzzing on 15 real-world programs that take 10 different file formats as inputs. The results show that ABAP Smart clearly outperforms the selected baseline in both branch coverage and bug finding. Notably, ABAP Smart doubles the number of bugs found, and in total, it discovered 42 zero-day bugs in the selected benchmark, in which 23 CVs were assigned. We have released our tools, and it quickly gained attention from both academia and industries. Our work has been featured on several media channels, and it has been reviewed and discussed in several different languages, including Chinese and Russian. This concludes my talk today. As our tool is freely available on GitHub, please give it a try and happy fuzzing.